Here is something that will bother you if you think about it carefully. You're sitting in a room right now. You have an intuitive sense of where things are, how fast they move, what time it is. If someone rolls a ball across a table, you can predict where it lands. If someone drops a cup, you know it will fall. You understand, without any training, roughly how the world works at the scale you live in. That intuition has been refined over hundreds of thousands of years. It is a finely tuned instrument, calibrated for exactly one thing: keeping a medium-sized primate alive on a planet with moderate temperatures, low gravity, and nothing moving anywhere near the speed of light. Outside those conditions, every single one of your instincts is wrong. Not approximately wrong, not wrong in ways that can be corrected with a bit more information. Structurally, categorically, irreparably wrong, in ways that cannot be made intuitive no matter how many metaphors you pile on top. This is not a failure of science communication. It is a feature of the universe. Modern physics is not the story of gradually refining common sense. It is the story of systematically dismantling it, piece by piece, and replacing it with something that works. There is a word for what physics actually does, and the word is abstraction. Not in the vague sense of difficult ideas, in the specific sense of replacing familiar concepts, things you feel you understand, with artificial constructs that have precise mathematical definitions and no necessary connection to anything you have ever seen or touched. A point mass, a field, a wave function, curved spacetime. These are not refinements of common sense. They are replacements for it. And here is the part that should genuinely astonish: the replacements work better, far better. They make predictions about the behavior of matter to 12 decimal places. They predicted objects and phenomena decades before those objects and phenomena were observed. They describe a universe that no human instinct had reason to expect. This is what physics has actually done in the last 300 years. And the most remarkable part is that at every step, the people doing the dismantling did not know where they were going. They followed equations. The equations led somewhere extraordinary. The universe, it turned out, was not designed to be understood by the animal that discovered it. Let's start at the beginning, not the beginning of the universe, but the beginning of the method. Before the 17th century, the physical world was understood only qualitatively. This is not an insult to the ancients. Greek mathematics was sophisticated, some of it genuinely elegant. But the idea that the physical world could be measured, that it was the kind of thing that submitted to numbers, that idea was mostly absent. Objects fell, planets moved, fire rose, water settled. These were qualities, not quantities. No one asked how fast an object fell. No one measured trajectories. It simply seemed to be the wrong kind of question to ask about matter. The ancient intuition was that nature's processes were inherently qualitative, that asking how much about falling bodies was like asking what color justice is. The physical world had its natures and its tendencies. Stones fell because earthly things seek the earth. Fire rose because fire is airy. These explanations satisfied the need for understanding because they connected phenomena to familiar categories. They told you nothing you could use to calculate anything. That was not seen as a deficiency. Then something changed. Newton decided to measure everything. He did not just make better observations. He introduced abstractions, artificial conceptual tools that do not exist in nature, but make calculation possible. A point mass, an object with mass but no size, no surface, no texture, a trajectory, an imaginary line that traces a path through space. An instantaneous velocity, a speed defined at a single moment in time, which requires inventing the mathematics of limits to define at all. Newton needed calculus before he could write down his mechanics, and so he invented it. None of these things are real in any direct sense. You cannot find a point mass in nature. You cannot see a trajectory. You cannot observe an instantaneous velocity. They are fictions, but they are precisely calibrated fictions, and they work. That is the crucial shift. The measure of an idea in physics is not whether it is intuitive or visualizable or satisfying to your sense of how things ought to behave. The measure is whether it gives correct numerical predictions when tested against the world. This sounds like an obvious standard. In practice, accepting it fully requires abandoning a very deep assumption that understanding something means being able to picture it. Newton proposed that everything in this room, your chair, the air molecules in your lungs, the phone in your pocket, knows the mass of the sun, and the sun somehow knows the distance to every object. From this knowledge, a force is calculated, proportional to the masses, inversely proportional to the square of the distance, a number, and objects move accordingly. Newton himself found this disturbing. He used the word absurd. How does the sun communicate across the vacuum? There are no strings, no rods, nothing in between. Action at a distance through empty space. Newton knew it sounded like magic. He wrote more than once that he had no hypothesis for the cause. He had only the equation, and the equation worked. Worked is an understatement. From a single formula, Newton derived everything Kepler had painstakingly measured over decades: the elliptical orbits, the relationship between orbital period and distance. All of it fell out of the algebra. And then more. The formula predicted orbit shapes that no one had ever observed, because no object with an unbound trajectory had been seen in the solar system. Hyperbolic orbits, trajectories that pass through the solar system and never return, came directly out of Newton's equations as valid solutions. The math said they should exist. 300 years later, an object came from outside the solar system, traced a hyperbolic path, and departed. The equation was right. The solution had been waiting in the algebra for 3 centuries before nature provided an example. This is a pattern that will repeat. You write down what you know. You treat it seriously, you discover. In the mathematics, solutions you had not anticipated. And the universe eventually produces physical examples of those solutions, demonstrating that the mathematics was describing something real all along. And then there is orbital mechanics, which provides a gentler illustration of how quickly common sense fails even within Newtonian physics. Imagine 2 spacecraft in the same circular orbit around Earth, one slightly ahead of the other. You are in the rear craft and want to catch up. Common sense says, fire your engine forward, accelerate, close the gap. If you do this, you will not catch up. You will move to a higher orbit where you travel more slowly and the gap will increase. To close with a spacecraft ahead of you on the same orbit, you must brake, firing your engine backward, dropping to a lower orbit where you travel faster. The math makes this completely clear. Astronauts must be trained explicitly on simulators to override the instinct that says speed up to catch up. This is Newtonian mechanics, the physics of the 17th century, the physics we find most intuitive, and it is already routinely counterintuitive the moment you leave the ground. There is a principle here worth pausing on. Once you have verified that a set of rules works in the cases you can test, you do not cling to them only where you are comfortable. You follow the algebra wherever it goes. You trust the math more than you trust your gut, because your gut was calibrated for a world that turns out to be a very small corner of the possible. The lesson from orbital mechanics generalizes. The deeper you go into a physical theory, the more thoroughly it violates the expectations of the animal that built it. Common sense is not just occasionally wrong at the edges. It becomes progressively less reliable the further you move from human scales in any direction. Consider what happens when you try to define the most basic concepts. What is matter? There is no definition of matter that does not use matter in the definition somewhere. What is space? If you try to define space as the arrangement of objects, you must define arrangement, which requires space. What is time? Any definition you attempt will require temporal language before, after, simultaneous rate to be coherent. These concepts are foundational. They are not defined in terms of anything more fundamental. They are the bedrock on which definitions are built. Wittgenstein called these the hinges on which our door of inquiry turns. Physics does not explain what space is. Physics describes the relationships between spatial measurements. It does not explain what matter is. It describes how quantities associated with matter, mass, charge, spin relate to each other and to measurements. The success of physics lies entirely in this, not in explaining what things fundamentally are, but in discovering the quantitative relationships between them. And these relationships, it turns out, can be discovered with enormous precision, and from them the behavior of complex systems can be predicted with extraordinary accuracy, without any underlying story of what the things relate to actually are. This is one of the strangest facts about the universe. We do not know what space is. We do not know what matter is. We do not know what energy is in any fundamental sense. And yet, by establishing the correct relationships between these undefined quantities, we can predict the positions of spacecraft to within meters after decades of flight, the energies of atomic transitions to 12 decimal places, and the timing of gravitational wave signals from merging black holes a billion light-years away. The universe, it appears, is made of relationships. The entities that participate in those relationships resist deeper examination. Push hard enough on any fundamental concept, and you reach a wall. Beyond the wall, there is only the observation that the concept exists, and that it relates to other concepts in specific ways. The relationships are everything. The next great demonstration of this principle came about 200 years after Newton, and it began with a bookkeeping problem. By the middle of the 19th century, the physics of electricity and magnetism had accumulated into a sprawling collection of experimental laws. Coulomb had measured how electric charges attract and repel. Ampere had mapped the magnetic fields surrounding current-carrying wires. Faraday had shown that a changing magnetic field creates an electric field. This is the principle behind every electrical generator ever built. Each of these was a well-verified, experimentally robust result, hard-won over decades of laboratory work by first-rate scientists. Then, James Clerk Maxwell decided to write them all down in a unified language. He had recently learned a new mathematical formalism, vector calculus, that described quantities with both magnitude and direction at every point in space. It was the natural language for fields, and electricity and magnetism were field phenomena. Maxwell translated all the known experimental laws into this language so that the relationships between them could be seen clearly. He did, and immediately discovered that they were mathematically inconsistent, not wrong in a subtle way, not off by a small experimental factor. He could show through pure algebra that the laws as stated were contradictory, that accepting all of them simultaneously led to a situation where the mathematics requires an impossible equality. A physical impossibility was embedded in the structure of known, verified laws. This should have been a crisis. Maxwell did something that exemplifies the scientific temperament at its best. He did not abandon the experimental laws. He did not go back and remeasure everything. He asked, "What is the minimum modification I could make to remove the inconsistency?" He examined where the logical gap was, and he added a single term to one of the equations, a term he called the displacement current, a term with no direct experimental basis, something he introduced specifically because the mathematics demanded something be there, and the contradiction vanished. But something else appeared in its place. When Maxwell looked at the new, consistent equations, he found that they contained solutions the original inconsistent versions could never have had. Certain configurations of electric and magnetic fields could sustain themselves, the two fields alternately generating each other, propagating together through empty space at a fixed velocity. He calculated what that velocity would be. It came from constants already measured in electrical and magnetic experiments that had nothing to do with light. The number he got was approximately 300,000 kilometers per second. This was, at the time, the known speed of light. Maxwell had not been trying to understand light. He had been doing bookkeeping. He found a contradiction and patched it, and the patch transformed physics. In one mathematical stroke, the nature of light was revealed, not because anyone had been looking for it. Light turned out to be an electromagnetic wave, a solution to equations written down to resolve an accounting inconsistency in the laws of electricity. The door to an entirely adjacent room had been opened by following algebra. Light, magnetism, electric charge, radio waves, all one phenomenon described by one set of equations. Heinrich Hertz confirmed this directly a decade after Maxwell's death, detecting radio waves in the laboratory and measuring their properties. The same equations, different wavelength. This is the pattern. You write down what you know. You treat it seriously. You discover contradictions or unexpected solutions. You follow them. The universe hands you something you did not ask for. The problem was that Maxwell's equations came with a built-in embarrassment. They predicted a fixed numerical velocity for light, the same number regardless of who was measuring or how they were moving. But according to everything Newton had established, velocities are relative. If you run toward a sound source, the sound approaches you faster. If you run away, it approaches you more slowly. This is how every wave and every moving object behaves. It is not even a sophisticated point of physics. It is obvious arithmetic. If you are moving at velocity v towards something moving at velocity c, the closing rate is v plus c. Common sense. First principles. The late 19th century spent considerable effort trying to rescue common sense. Perhaps light travels through some medium, a luminiferous ether, and Maxwell's equations describe the speed of light relative to that medium. Perhaps the equations hold perfectly only for observers at rest relative to the ether, and the ether provided a kind of absolute frame against which all velocities could be ultimately measured. This was not an unreasonable position. All known waves propagated through some medium. Sound needs air, ocean waves need water. Why should light be different? The Michelson-Morley experiment was designed to detect the Earth's motion through the ether. It was an instrument of extraordinary sensitivity, a device that split a beam of light, sent the two halves along perpendicular paths, and measured whether they returned at different times. If the ether existed and the Earth moved through it, there would be a slight headwind effect in one direction. The interference pattern of the recombined beams would shift by a measurable amount. The experiment was repeated multiple times in different seasons, with the Earth moving in different directions relative to the Sun. The interference pattern did not shift, not by a measurable amount, not by anything. The speed of light was the same in every direction, regardless of how the Earth was oriented or moving. The ether did not exist. Common sense had no escape route. The resolution was Einstein's, and it began not with an experiment, but with a question. What if Maxwell's equations are simply correct as written? What if the speed of light really is constant for all observers? Not because of some clever mechanism, not because of some property of the ether, but as a fundamental postulate, a law of nature as basic as the conservation of energy. Accept it, write it down, follow the implications. What comes out is the end of absolute time. Consider a simple thought experiment. Someone on a moving train shines a laser straight up at a mirror on the ceiling. The laser pulse travels up, bounces, comes back down. From the perspective of the person on the train, the light takes a certain amount of time to complete this round trip. Let's call it t. Now watch the same experiment from the perspective of someone standing on the platform as the train goes by. From their vantage point, the light does not travel straight up and down. It travels diagonally up and forward to reach the mirror, which has moved during the transit, then down and forward as the floor of the train catches up with the returning pulse. The path is longer, geometrically measurably longer, the diagonal of a triangle rather than its vertical side, but the speed of light is the same for both observers. Speed is distance divided by time. If the path is longer for the platform observer, and the speed is fixed, then the time must be longer. The same physical process, the light making its round trip takes more time according to the platform observer than according to the passenger. This is not a measurement illusion. There is no sense in which one observer is right and the other wrong. Both are measuring correctly. Time itself runs differently for the moving observer. A moving clock genuinely runs slower than a stationary one. The discrepancy is exactly calculable from the geometry of the triangle, using nothing but the Pythagorean theorem and the constraint that light speed is constant. The effect is small at everyday velocities. A car traveling at highway speed carries a clock that falls behind a stationary clock by a few nanoseconds per day. But at velocities approaching the speed of light, the effect becomes enormous. Right now, particles called muons are being produced in the upper atmosphere by cosmic rays. They travel toward Earth at roughly 99% of the speed of light. Muons are unstable. They decay in about 2 microseconds in their own rest frame. At the speeds they travel, they should decay long before they reach sea level. The geometry says they have time to travel only a few hundred meters, not the 20 kilometers from the top of the atmosphere to the ground. They reach the ground anyway, in measurable quantities, detected in particle physics experiments around the world. Their clocks run slower by a factor that depends on their velocity, exactly as the relativistic formula predicts. From the muon's perspective, incidentally, there is no paradox. The muon is stationary, and it is the Earth that is rushing upward. The 20 kilometers of atmosphere contracts in the muon's frame to a distance the muon has plenty of time to traverse. 2 different explanations, time dilation for the ground observer, length contraction for the muon, give the same physical result. The muon arrives. The consistency between these 2 descriptions is not accidental. It is a fundamental feature of special relativity, and it provides a worked example of how apparently paradoxical conclusions resolve when you follow the logic carefully. Consider a more dramatic version. There is a famous thought experiment involving a train that is longer than a tunnel. At rest, the train does not fit, but if the train moves fast enough, its length contracts along the direction of motion from the perspective of the tunnel operator. At sufficient speed, the contracted train fits inside the tunnel. The operator can, in principle, simultaneously slam shut both sets of tunnel gates, and the train will be entirely inside. But from the driver's perspective, the train has not contracted. In the driver's frame, the train is at rest and the tunnel is moving. A moving tunnel contracts. The situation is worse than before. Surely one of them is wrong? Neither is wrong. What changes is the meaning of the word simultaneously. The tunnel operator closes both gates at the same time. But the driver does not agree about which events are simultaneous. For the driver, the front gate closes and opens first, while the locomotive is still approaching it, and the rear gate closes and opens later, after the last car has passed through. There is no moment in the driver's frame when the entire train is inside the tunnel, so no contradiction arises. The gates operate as described, nothing collides. The frame-dependent accounts are both correct. This resolution, that simultaneity at distant locations depends on your state of motion, is not a logical trick. It is a structural feature of the universe. Events at 2 separated locations that are simultaneous in one frame will, in general, not be simultaneous in another. There is no universal now. There is no absolute sequence for events that are not causally connected. This is experimentally verified constantly in particle physics experiments, in GPS satellites, and in precision atomic clock experiments. All of this followed from accepting 2 premises: that the laws of physics are the same for all observers in uniform motion, and that the speed of light is the same for all of them. 2 sentences, neither of which sounds dramatic. What they imply is a demolition of everything Newton assumed about the nature of space and time. That space is an unchanging backdrop and time flows uniformly everywhere at the same rate. Both assumptions are wrong, neither can be rescued. And then came gravity, Newton's gravity had worked extraordinarily well for 2 centuries, but it had always carried a philosophical embarrassment. The sun exerts a force on the Earth across 93 million miles of empty space. Nothing travels between them. Nothing connects them. And yet the force is felt instantaneously, at least according to Newton's formulation. Change the sun's position and the Earth's orbit would change simultaneously, with no delay for the influence to propagate. Einstein found this unacceptable after special relativity. Special relativity established that no influence can propagate faster than light. Newtonian gravity, taken literally, involved infinite propagation speed. The theories were incompatible. Something had to change. The key ingredient came from mathematics developed decades before anyone imagined it would be needed. In the 1850s, Bernhard Riemann gave a lecture in Göttingen, his qualification lecture for a university position, attended by his mentor Gauss, in which he developed a completely new way of thinking about geometry. Euclid's geometry describes flat space. Parallel lines never meet. The angles of a triangle add to exactly 180 degrees. The shortest path between 2 points is a straight line. Riemann asked, what if these properties do not hold? What if space is curved, and curved differently at different locations? He developed the mathematics to describe such spaces in any number of dimensions. Crucially, he showed how the curvature could be detected and measured from within the space, without needing an external perspective. An ant walking on the surface of a sphere cannot step off the sphere to see that it is curved, but it can discover this by drawing large triangles and measuring their angles. The angles will exceed 180 degrees by an amount that depends on the size of the triangle and the curvature of the surface. The geometry is intrinsic. It is in the space, not imposed on it from outside. Gauss was apparently so impressed that he remained silent after the lecture, which for Gauss was the highest available form of praise. Einstein used Riemann's framework to reformulate gravity entirely. The central idea is this: matter, mass, energy, pressure, curves the spacetime around it. Objects moving through this curved spacetime follow the most direct paths available, the geodesics, which are the equivalent of straight lines in curved geometry. What we perceive as gravitational attraction is not a force at all. It is the natural motion of objects following straight lines through curved spacetime. The sun does not pull the Earth. The sun curves the spacetime around it. The Earth follows a straight path through that curved spacetime, and that path happens to be an ellipse in three-dimensional space because of the way the curvature varies with distance. This requires accepting a picture in which time is a dimension woven together with the 3 dimensions of space into a 4-dimensional structure. Objects do not just have positions, they have world lines, threads drawn through spacetime that represent their entire history. The trajectory you observe in space is a shadow of the world line, a projection into 3 dimensions of something that properly lives in 4. Einstein's field equations, written in 1915, express the relationship between geometry and matter in a compact but extraordinarily powerful form. On one side, a mathematical description of how spacetime is curved. On the other, a mathematical description of how matter and energy are distributed. The equation says these 2 things must be equal. This is the law, the universe, at every point, at every moment must satisfy it. The predictions that follow are extraordinary, and several of them were made before any observation could confirm them. Light, Einstein showed, should bend around massive objects. The photon has no mass, but it must follow the geometry of the spacetime it travels through and near a massive object. The geometry is curved. The amount of bending is calculable. In 1919, an expedition to observe a solar eclipse measured the apparent positions of stars near the sun's edge. The stars appeared displaced from their catalog positions. The displacement matched Einstein's prediction and was twice the value that Newtonian gravity would have given, confirming that something beyond Newton was at work. Clocks at different distances from a gravitational source run at different rates. Deeper in a gravitational well, time passes more slowly. This is not a small effect in practical terms. GPS satellites orbit at altitudes where the gravitational time dilation and the velocity-based time dilation of special relativity both contribute. If these effects were not corrected for, GPS coordinates would drift by kilometers per day. They are corrected for precisely. The corrections are derived directly from Einstein's equations. The equations also predicted black holes, regions where space-time curvature is so extreme that even light cannot escape. This prediction appeared in the mathematics almost immediately after the theory was published. Einstein himself did not believe black holes were physically real. He thought they were mathematical pathologies, solutions that would be excluded by some physical principle he had not yet identified. He was wrong. Black holes are everywhere. The center of our galaxy contains one with a mass 4 million times that of the Sun. The photograph of its shadow, taken by a network of radio telescopes spanning the Earth, revealed a structure that matched the predictions of general relativity in detail. Gravitational waves, ripples in the curvature of space-time itself, propagating outward from accelerating masses, were predicted in 1916. They were not detected until 2015, nearly a century later, using laser interferometers capable of measuring a displacement of 1,000th, the diameter of a proton across arms 4 kilometers long. The signal that was detected in September of that year came from 2 black holes, each around 30 solar masses, spiraling into each other and merging more than 1 billion light-years away. The merger lasted about 1/5 of a second. The wave arrived on Earth as a distortion in the geometry of space itself, stretching and compressing the arms of the detector by that subnuclear amount. The waveform matched the prediction of Einstein's equations computed for black holes of those masses at that distance, essentially perfectly. The equations also described the large-scale behavior of the universe. In the 1920s, a Soviet mathematician named Alexander Friedmann solved Einstein's equations for a universe that is roughly the same in all directions, without any special center or preferred location. He made no assumption about whether the universe was static or dynamic. He simply let the equations decide. They decided that all distances in such a universe must either be increasing or decreasing. They cannot remain constant. The universe, according to general relativity applied without prejudice, cannot stand still. When Edwin Hubble measured the velocities of distant galaxies, he found they were receding, more distant galaxies receding faster. This confirmed the expansion. The universe is not static. Distances are growing. This expansion is not a movement of galaxies through space. It is a change in the distances of space itself. The distinction is not trivial, and it is the most consistently misunderstood feature of modern cosmology. Think of a notebook filled with letters, A, B, C, D, extending to the left and right without end, 10 millimeters between each neighboring pair. Overnight, the notebook doubles all distances. Tomorrow, A and B are 20 millimeters apart. But so are every other neighboring pair. The distance between A and the letter 10 steps away is now 200 millimeters, twice what it was. The distance between A and the letter 100 steps away is now 2,000 millimeters, twice what it was. From the perspective of any letter, every other letter is receding. Letters farther away are receding faster because there is more total space between them that is all expanding. A letter 50 steps away is receding twice as fast as a letter 25 steps away. A letter far enough away is receding at a rate that, computed naively, exceeds the speed of light. This does not violate special relativity. Special relativity prohibits objects from moving through space faster than light. Here, space itself is expanding. No letter is moving through space at all. The expansion of space is not subject to the light speed limit that governs motion through space. Objects beyond a certain distance, called the Hubble horizon, are simply unreachable, regardless of what you do, because the space between you and them is accumulating faster than light can traverse it. These objects are not moving away. The distance to them is growing. The distinction is real and physical. Every letter in the notebook thinks it is the center of the expansion. None of them are the center. There is no center. The expansion is everywhere, intrinsic to the space, not spreading into anything outside it. Running this expansion backward in time, in the early universe, all distances were smaller. Not because everything was packed into a small volume in the middle of existing space, but because space itself was denser. The hot, dense, early state of the universe was not a point in space from which things exploded. It was a state of all space, everywhere simultaneously. Every region of space was at that density at that moment. This is what the Big Bang actually is, a moment in the past, not a location. There was no empty space outside it into which the universe expanded. The universe encompasses its own expansion from inside. Every picture of the Big Bang as a fireball expanding outward from a central point is wrong. Not approximately wrong, fundamentally wrong. The error is treating an event in time as an event in space. The Big Bang is not a place, it is a time. And the space that existed at that time was already infinite, or at minimum very much larger than anything we can observe, because the space we observe today, which is extremely large, was compressed, not packed into a mathematical point. Now we descend further past stars, past atoms, past nuclei into the quantum. The failure of classical physics at small scales was apparent by 1900. Hot objects emit light in a specific distribution of colors and intensities, and classical physics predicted a distribution that diverges to infinity at short wavelengths, an infinite amount of energy in the ultraviolet part of the spectrum, which is obviously not what is observed. Atoms have sharp spectral lines, they absorb and emit light at specific wavelengths only, and classical physics gave no account of why. And most devastatingly, classical electrodynamics predicted that an electron orbiting an atomic nucleus must continuously emit radiation, lose energy, spiral inward, and collapse onto the nucleus in a fraction of a microsecond. Atoms cannot be stable, matter cannot hold its structure, everything around you cannot exist. This was not a minor discrepancy, it was a complete failure. The classical framework, however successful at everyday scales, gave answers for atomic structure that included the non-existence of atoms. Something was deeply wrong. Quantum mechanics was built by abandoning, one by one, the assumptions that make atomic physics impossible. The replacements are not intuitive, they cannot be made intuitive. They describe a layer of reality so different from the world of human experience that every analogy eventually breaks down, and the analogies that seem helpful at first often become actively misleading. The first step was accepting that energy comes in discrete chunks. Max Planck introduced this idea in 1900 as a mathematical trick to make the blackbody radiation formula work. He himself considered it a provisional artifice, not a fundamental description of nature. Einstein took it seriously and used it to explain the photoelectric effect, for which he won the Nobel Prize. Light hits a metal surface and electrons are ejected. The energy of each ejected electron depends not on the brightness of the light, but on its frequency. Classical physics predicts that increasing intensity should increase electron energies. Observation says otherwise. Einstein's explanation, light consists of discrete packets, photons, each carrying energy proportional to frequency. A photon either has enough energy to knock out an electron or it does not. Brightness determines how many photons there are, not how much energy each carries. The electron, when examined more closely, turned out to have its own discrete character. Niels Bohr proposed in 1913 that electrons in atoms occupy specific energy levels and can only absorb or emit light in precise amounts corresponding to transitions between levels. This model was incomplete and conceptually inconsistent, but it reproduced the spectral lines of hydrogen with remarkable accuracy. It was enough to demonstrate that something genuinely new was at work. The full theory came in two independent forms in 1925 and 1926. Werner Heisenberg, recuperating from hay fever on a remote North Sea island, developed matrix mechanics, a formalism in which physical quantities are represented not by numbers but by arrays of numbers, by matrices that do not in general commute. The order of multiplication matters, and this non-commutativity turned out to be the mathematical signature of the uncertainty principle. Erwin Schrödinger, on a Christmas holiday in the Swiss Alps, developed wave mechanics independently and from entirely different premises. His starting point was the idea that particles might have wave-like properties. The two formalisms appeared contradictory. Within months, it was shown they were mathematically equivalent. Different languages describing the same underlying structure. The uncertainty principle, formulated precisely by Heisenberg in 1927, is not a statement about the limits of measurement. It is not saying that instruments disturb the systems they measure, that a more careful or gentler measurement could bypass the issue. It is a statement about what properties exist. Position and momentum cannot both have precise values simultaneously. This is not an observational limitation, it is an ontological fact. The universe does not contain the information that would be needed to specify both simultaneously. An electron in a stable atomic orbit does not have a position. Not an unknown position, not a hidden position, not a position that exists but eludes measurement. It has no property of being located at a specific point in space. What it has is a mathematical description, the wave function that assigns probability amplitudes to different measurement outcomes. If you interact with the electron in a way that constitutes a position measurement, you get a specific result. But that result was not determined before the measurement. The measurement creates it. Before the measurement, only the probability distribution existed. The wave function is not a description of our ignorance. It is not a bookkeeping device for tracking probabilities in the way that you might describe the probability distribution of a coin toss, where the coin has a definite state at all times, and the probability only reflects your incomplete knowledge. The wave function is the complete description. The electron is genuinely maximally described by the wave function, and the wave function does not assign it a definite position. This makes trajectories impossible. A trajectory is a series of positions, each tagged with a velocity that is the derivative of position with respect to time. If positions and momenta cannot both exist simultaneously, trajectories do not exist. Electrons do not fly around nuclei on paths. They do not fly in any meaningful sense. There are probability distributions that describe where a position measurement would find them. There are interference effects between different parts of the probability amplitude, but there is no small charged ball tracing a curve. This is why atoms are stable. If electrons had definite positions and velocities, they would accelerate, radiate electromagnetic energy, and spiral inward. Because they do not have definite positions or velocities, there is no trajectory on which this collapse could take place. The minimum energy state of the hydrogen atom has a specific spatial extent, the Bohr radius, because the uncertainty principle prevents the electron from being localized more tightly without granting it enormous momentum, which costs energy. Atoms are not stable despite quantum mechanics. They are stable because of it. There is a second fundamental feature of the quantum world that is entirely distinct from uncertainty, and just as disorienting, genuine, irreducible randomness. Quantum mechanics predicts probabilities. But the probabilities are not expressions of ignorance about hidden variables. They are the fundamental description. Take two electrons that have been prepared in identical states, and this can be done. Quantum mechanics permits the preparation of states so well defined that the electrons are genuinely, in principle, indistinguishable, not merely similar, but truly the same. Subject both to identical measurements in identical experimental setups. The results in general will differ, not because the electrons are secretly different, not because of hidden variables you have not accounted for. The outcomes are not determined in advance. The universe does not decide which result each electron will give until the measurement happens. The randomness is not reducible to incomplete knowledge. It is built into the structure of physical law. John Bell proved in 1964 that no theory of hidden variables, no theory in which quantum systems carry definite properties before measurement, and these properties determine measurement outcomes, can reproduce all the predictions of quantum mechanics. Experiments have since confirmed the quantum mechanical predictions, ruling out a very broad class of hidden variable theories. The randomness is not ignorance, it is fundamental. There is a theorem that goes even further, the Cochin-Specker theorem, and it concerns the consistency of pre-existing values across different measurement contexts. Suppose you try to assign definite values to quantum properties before any measurement occurs. You want the properties to be real, like cards in a deck, with their values fixed, just hidden from you until revealed. The Cochin-Specker theorem proves that no such assignment can be made self-consistently. Any attempt to assign definite values to all quantum observables leads to a contradiction. The problem is not just that we cannot observe the values simultaneously. The values cannot exist simultaneously in a logically consistent way. What this means is subtle and radical. The answer you get when measuring property A depends on which other properties you measure alongside it. Not because measuring B physically disturbs A, but because there is no fact of the matter about it independent of the measurement context. The property A does not have a value until you set up an experiment that can reveal it, and what that experiment also asks about changes what A's value turns out to be. Quantum properties are contextual. They do not belong to objects. They emerge from the interaction between objects and measurement arrangements. This is not how anything in ordinary experience works. In ordinary experience, the properties of an object, its color, its mass, its temperature, belong to the object. They exist whether or not you are looking. In the quantum world, this is not true for a wide class of properties. The properties are partly constituted by the measuring process. This should be genuinely disturbing. It is not made less disturbing by familiarity. Physicists who have worked with quantum mechanics for decades find, when they stop to think about it carefully, that it is still deeply strange. And yet the predictions work. This is the astonishing part, and it deserves to be stated carefully. The magnetic moment of the electron is a quantity that describes how the electron responds to a magnetic field. It is a single number. Quantum electrodynamics. The quantum theory of the electromagnetic force predicts this number through calculations involving diagrams, representing all the ways an electron can interact with virtual photons and other particle-antiparticle pairs flickering in and out of existence. The calculation at high precision involves tens of thousands of such diagrams. The result has been computed to 12 significant figures. It has been measured in exquisitely precise experiments to 12 significant figures. The agreement is complete within experimental uncertainty. No other scientific theory has achieved anything close to this precision in any domain. The theory that describes a world with no trajectories, no definite positions, irreducible randomness, and measurement contextual properties gives numerical predictions that match reality to a part in a trillion. The method that achieves this is worth examining because it looks nothing like physics instruction often suggests. You do not start with a picture of what the electrons are doing. You do not ask where the electron is at each moment. You write the quantum state of the system as a vector in an abstract mathematical space, a Hilbert space of potentially infinite dimension. You let it evolve according to the Schrödinger equation, which describes how vectors in this space change in time. The electron is nowhere in this description. There is no electron flying through space. There is a vector evolving in an abstract mathematical space. At the end, when you want to know what a measurement would yield, you extract probability amplitudes from the vector and square them. You get a probability distribution over possible outcomes. You run the experiment, you check. What is happening in the physical world between preparations and measurements? The theory does not say. It provides a calculation procedure that predicts the statistics of outcomes. The procedure works with unequaled precision. What it corresponds to physically, what the wave function represents in terms of real physical entities, this remains genuinely debated 100 years after the theory was written. Quantum mechanics is also why the periodic table exists. Chemistry is not just an empirical catalog of what reacts with what, it has a